Now at this point, our simulation is looking quite cool, and we can go ahead and start running some higher res simulations for this. So going back into our setup, let's go to our flip source here, and I'm going to try a particle separation of 0.04. If you display our source particles here, now you can see that this is generating 6 million source particles for the sim, so this should be nice and high resolution. And we can also increase the resolution of some of the miscellaneous volumes involved in this setup. So if you go back inside our DOP.NET and look at the flip object, you can see that we have this grid scale option here, which means that the volume fields used in our fluid solve are going to be half the resolution of our particle separation. So the voxel size is twice our particle separation here based on that grid scale of 2. So we can change the voxel size on our flip source over here. In this flip source, I'll copy the particle separation parameter, paste the relative reference into the voxel size, and then multiply that particle separation times 2. So now the voxel size is 0.08, but if you display the source volume after our split here, you can see this still has a voxel size of 0.1. I'm guessing that's because we have an input volume of voxel size 0.1, so let's rerun our input volumes that are creating the source region here, and these VDB from polygons that are used to generate the source region are already channel linked to the flip source voxel size. So if we go to our cache river source and change this version on the file name to be version 2, or you could call it high res or something instead if you prefer, let's save that to disk. And now after recaching this river source region, that voxel size is 0.08 as we expect, and we're seeing the same thing on the source volume after the flip source and after the split. This is now a voxel size of 0.08 as well. And I suppose we don't really need to increase the resolution of our boundary volumes and our flow volumes here. These don't really have to be high res. With the flow volume in particular, if you display the visualization for that velocity volume, we're not going to really get any better velocities by having this be a much higher res volume. If you were to introduce some more randomization to this to break up those velocities a bit, then perhaps there could be some benefit toward increasing the resolution of this velocity flow volume. But since it's just sort of a general flow, the lower res volume does give us enough detail. And I should also point out that since we really increased the number of particles going into our volume trail here, this is very slow to display this volume trail with 6 million particles. That's really overkill. So you could speed up this visualization a bit. Instead of just using all of those 6 million source particles to display this volume trail, we could possibly generate some new display particles from our source volume here. So if you want to keep your scene really clean and you don't want to merge in the source volume, then we could disconnect the volume trail there. And then you could object merge in the source volume here. Point that object merge to ... /source volume. And this will give us the volume for the region that we're using for the flip source. So display that. And then we can generate some new particles here for use in our volume trail. So let's try a pyro source. I'll set the mode to volume scatter, connect that to our source volume, display the pyro source, and then we can go with a lower particle separation here. And a lower particle separation can actually help us to see a bit better what's happening in these flow volumes. So a low particle separation of 0.5 looks like it gives us enough points to really see what's happening in this flow volume here. So then plug that into the volume trail and then display that. And now we can see this trail much better than we could before when it was just a solid block of points. And you can see that we don't really benefit from higher resolution on some of these fairly simple volumes like this. Unless you start adding in some randomization or noise, then yeah, we're not really going to benefit by cranking up the resolution of this volume here. I should also add that if you don't like this evenly stacked grid of pyro source points, then we could also jitter this a bit for our visualization. So I'll drop in a point jitter, and I'll use the particle separation amount on the pyro source, copy that parameter, and then paste a relative reference into the scale on the point jitter. So that'll give us an appropriate amount of point jitter on those display points that matches up with the amount of particle separation in the pyro source. And since we've made all of the volumes in our setup higher resolution by turning down this voxel size here, it's totally fine to leave that higher resolution on these flow velocities and the boundary velocities here. But because the simulation doesn't really benefit from that added detail in these areas, it's totally fine if you want to unlink these from the flip source voxel size. So if we select all of these VDB from Polygon nodes that are associated with building these boundary volumes, grab those sync VDBs there, boundary surface VDB here, we can then Control-Shift-Click the voxel size to get rid of that channel reference, and I'll Control-Middle-Click the voxel size to set that back to its default value. It's totally fine to leave these volumes at that slightly lower resolution, because that's not really impacting the detail of our sim. We can do the same thing on the volume rasterized attributes nodes for this boundary velocity and for our flow velocity here. Control-Shift-Click the voxel size for those volume rasterized attributes nodes, and then Control-Middle-Click this voxel size to set it back to its default value. Of course, you don't need to use the default values for these things. You can set that to whatever you feel like your scene calls for. And although it doesn't matter too much what you set the boundary and flow volume resolutions to, it does make a big difference what you set your collision volume resolution to. For these colliders, this volume resolution has a very real impact on the quality and accuracy of the sim. You don't need to expect a super crisp representation of all of the detail in all of your colliders when viewing this collision volume, but we can do a bit better than this. This collision source is already linked to the voxel size in the flip source, so that's picking up this slightly higher resolution of 0.08, but our cached version has this larger voxel size of 0.1, so let's version up that collision volume file name and then save that to disk. And if I switch between these two cached out files, there's not a massive difference from version 1 to version 2 of our collider, but version 2 does give us a bit better detail, and it should better represent the collisions with all of the rocks. And you could try pushing the resolution of your collision volume higher, but you won't necessarily benefit from that additional resolution because the Flip Solver's own processing is working at a specific resolution, and pushing our collision input higher than that won't really add any extra detail on top of what the Flip Solver is using. So now that we've up-resed our collision volume and up-resed our source particles, let's go ahead and set up some caching for the sim. I'm going to rename my DOPNet to river_sim, and then we can import the data from this with a DOP import fields. Let's drag and drop the river sim into the DOP network name parameter. And for the default object, we want to bring in the flip object, so we'll just type in flip star, which will import any object with flip at the beginning of the name. And then for the presets, we'll choose flip fluid. So this brings in our particles via the geometry here. It brings in the representation of the surface of this fluid, which is a volume, and it brings in our velocity volume data as well. So we can display that. And if you middle mouse on the DOP import field, you can see all 6 million particles, but our volumes are only a voxel or two large because our simulation needs to evaluate a frame before it gives us meaningful data for this surface and velocity. And if you step forward one frame, you can see that now these surface and velocity volumes are large volumes including the entire river region. And between these volumes and the 6 million particles, this is a lot of data to store, and it can take up quite a lot of disk space and RAM and etc. So there are ways to optimize this as we save it to disk. So we have this very helpful fluid compress SOP. We can drop that in, connect it to our DOP import field. And this does a few different types of optimization. This will pack our data in an optimized way. It'll compress our volumes to 16-bit floats. It throws away some unnecessary attributes. And one of the most important things it does is this will remove particles that are inside the main body of the fluid by a certain depth. And we don't really have to worry much about the settings on the fluid compress. The one that we really have to watch out for is the particle separation. So we're going to link that to our fluid source as well. So back on the flip source here, right click and copy that particle separation parameter, then go down to the fluid compress and paste the relative reference into the particle separation here. And this doesn't look like much of anything in the viewport, but we do have tools at our disposal that expect this type of input that can process that correctly and also display it nicely. So if you drop in a particle fluid surface, we have a few different options for the output of this. On Convert To, I'll select Particles, and I'll turn on Velocity Visualization. So now you can see all the particles at the beginning of our sim here. And if you zoom in, you can see that the middle of this particle sim has been hollowed out. So we're not storing all the particles in the middle of this body of fluid, which is totally fine because we don't really need all of that data when we're meshing this. So it's totally fine to throw that out and optimize our disk caches a bit. And that's a very helpful bit of optimization that this fluid compress applies. And the particle fluid surface does expect this type of input, so once we move on to meshing this, you will correctly get just the exterior of the surface meshed, but we'll take a look at that some more later. So now let's disconnect the particle fluid surface and add in a file cache. Let's connect that to the fluid compress, and I'll rename this to cache river sim, and I'll point this to my geo/river directory and make a wide shot river v1 directory as well, and then I'll make a folder in here called sim, and I'll set the file name to river_sim.$f3.bgeo.sc. And looking back at our latest simulation, you can see that this takes a little bit of time in order for this to settle into some natural motion and start looking nice. It looks like it takes around 30 to 50 frames before it really starts looking nice. So we're going to need to simulate some extra frames so that we can time offset this afterwards. So back on our start and end frame for the file cache, I'll Control-Shift left click that to get rid of that expression, and let's cache this up through frame 300. So we've set the file path, set the cache range to 300, now let's turn on load from disk, and then hit save to disk to cache out the high-res sim. Now it took a few hours to cache out this entire high-res simulation, but after that finished caching out, we can display this particle fluid surface node with the output set to convert to particles and the velocity visualization turned on. And then after flipbooking that, we get a result that looks like this. So this is looking really cool. We have tons of nice detail in here. It's very organic, natural flowing motion, and I'm really happy with how this is looking. If I were being very critical, I'd say perhaps the stick on the sides is a little bit too strong. It looks like where it's contacting the colliders, it's kind of holding on to those particles a bit too strongly, but once this is meshed and rendered, you don't really notice that. You can certainly feel free to turn down the stick on collision or tweak whatever things you'd like, but overall, I'm happy with how this is looking, so let's go ahead and start meshing the simulation.